Hey, so welcome back, and this is another daily LeetCode problem. So this one was called largest color value in a directed graph. So let's take a look at it. So it's a hard problem, and you're given a directed graph here with different colors and different numbers. Now the numbers aren't really important, they just indicate the kind of ordering of the node, but the colors themselves is what we want to be concerned with. The other catch here is that you can have like cyclic dependencies, so you do have to handle cases where there's a cycle. And so what you're given is you want to find out what is the largest color value of any valid path. And that just means at any point in this graph, what is the kind of largest consistent number of colors that you have, or the color value of the color that appears the most in that particular path. So in this case, if we're looking at it, we can see that, okay, by going down this path from left to right, we can see that the color red appears 3 times in these cases, while the color blue here only appears once. There's also a second path here, but that would only give you a color value for the color red of 1, and purple would be 1 as well. And so the only other case that they show you here is, okay, well, if you have the cyclic dependency, then we just want to return -1 because we don't really want to consider this. This would end up kind of becoming infinite because it would keep iterating. And so in that case, they just want you to say -1. Okay, and so really, like in any case where there is a cyclic dependency, like let's say like you were able to go down a particular path this way, and say with these were all red, you'd still want to say -1 in this case and not consider this path because there is a cyclic dependency in the graph. So you just say, okay, it's -1. All right, so there's a lot of ways you can implement this. The most intuitive way for me was using something called topological sort. And this is kind of just famous like graph theory that you might learn in university or just kind of looking at YouTube videos online. But it's called topological sort. But more specifically, the algorithm that we're going to be using is like Kahn's variation of it. And so this is often, I think, the most popular explanation for this is when you're dealing with like course scheduling. So like you can't take algorithms 2 until you take like the first algorithms class, or you have to take Java, like your first Java class, before you can take like a system design related class or something. So it's finding out, okay, you're given a DAG, and that's like directed acyclic graph, and you want to find out, okay, what order can we do these courses in? So like course A, course B, and course C here. And so say the DAG kind of looks like this, and say we have course D over here. And so in this case, you're going to want to say, okay, we would probably want to take the courses in like course A first, and then B, and then maybe D, and then C. But you could also do D or B in that order, or you could also do D and B at the same time, because this graph kind of represents the dependencies. And so using topological sort, you can kind of figure out, okay, given this directed acyclic graph, like what order would I want to take these courses in? Now it has to be like acyclic graph because, well, in that case, say you can't really take a course if its own dependency is itself. And so that is what would look like this here. And so these algorithms also want to be able to check and see if there is in fact a cycle in the graph. And if so, you're able to really easily just like in that graph natively just return -1. All right, and so that's kind of the exact approach that we're going to take. We're going to take this algorithm and modify it so that we can solve this problem. And it's great because it can really easily see if there's a -1 in the cycle, but then also like travel this graph from like the root to its nodes. And we can propagate this path in the kind of max color value as we iterate down this path. All right, so let's go ahead and do it. So what we're going to do is we're first going to represent this graph using some data structure, and in this case we're going to use an adjacency list. So let's go ahead and do that. So we'll just, I like to call it like this. And typically you want to use a default dictionary. And just for practice, let's import it. Great. And so the second thing that we're going to want to do is also we're going to be using something called in_degree. And so this is just to represent at every single particular node how many incoming edges do we have for that node. And so if we look at this node, we would have an in_degree of 1 because there's only one incoming edge. Okay, and that's how we kind of be able to see, okay, what are the dependencies that are like, what are we dependent on? So what has to come before us before we can proceed? Because if we have any edges that are pointing to us, those have to happen first before we can take this course. So these kind of represent, okay, say course D, you must take course A, B, and C before it, then it would have 3 in_degree in it because 3 incoming edges, those 3 courses. Okay, so let's go ahead and populate this. So for every source and destination in our edges, because the graph is kind of represented using this 2D array where you say, okay, course or like node 0 points to node 1. And so in that case, we want to iterate through that array and build our graph representation. Great, and so from here, let's go ahead and do that. So what we'll see is at this particular node in our adjacency list, let's append that destination. So we can say, okay, S can go to this particular node. But then also we want to update our in_degree. So we can say, okay, the in_degree of this particular node, let's see here, D, and we're going to want to increment it. So let's add 1. And so this will actually be an integer in this case. And so what this means is, okay, at this particular destination, since S points to D, this destination, then we can increment and say, okay, there is 1 extra incoming edge to this particular destination. Great, and so for Collins' algorithm, you want to build out a queue, and initially you only want to add to the queue the roots or things that have like no incoming edges. And so if the in_degree is 0, then you know that that's kind of like a root node of a graph. Like that's a starting point where, okay, say course A is like the first course you would take at your university, then it would have no incoming edges because nothing, you don't have to take anything before it. There's no prerequisites. So let's add to our queue nodes without any prerequisites. Awesome. And so from here, let's go ahead and iterate through here. So for every, I believe it's for I in our range of nodes here. So let's go ahead and we'll probably end up using this quite a bit. So let's just get the length of these colors. So this just represents, okay, how many nodes do we have in our graph? Because you'll have a color for every single node. And so for this particular range, let's create our queue here. Queue. We'll do a stack. And so from here, let's go ahead and say, okay, if at this particular node, the number of incoming edges is 0, then we want to add it. Okay, and so I'm just going to move myself up here to give us more room. And so let's go ahead and add to our queue that, okay, at this node, we want to process it because there's no prerequisites. Awesome, so that's step 2. And so next, what we want to do is, while we have something on our queue, we're going to want to process it. And what we're expecting in return is some response, which initially we're going to set to 1. And that's because, well, we're going to always want to return at least 1 in the cases where there's no cyclic dependency, because you're going to have at least one color for that node. So if you have one node and it goes nowheres, then, well, okay, you're going to want to return at least 1. And then we're also, for Khan's algorithm, you have something called like the count or the visit count, and it's initially 0, and this is supposed to represent the number of nodes that you visited. So typically for graph algorithms, you use like a visited set, so you don't have like this recursive nature where you just keep infinitely checking nodes. But we don't have to worry about that using Khan's algorithm, because you're never going to, so for this one, you're actually never going to visit anything. You're just going to immediately return -1. Because this node has an incoming edge, it doesn't have an in degree of 0. It has an in degree of 1 here. And so nothing's going to be added to this queue, so we're not actually going to process anything. So we're just going to automatically return our result. Okay, so the way you check that is say, okay, if the number of nodes that we visited is not equal to the number of nodes, then we know that there's a cycle. So to write that out, if our count does not equal n, or is equal to n, then we want to return our result. Otherwise, let's just return -1. And that's because, well, any single part of our graph, even if it's like split into different graphs, like kind of different groups, you won't even visit the graph. Say graph A has a cycle, you're never going to visit it because you won't have a starting point, because there will be some cyclic dependency there. Great. And so let's continue on. So let's get our current node, and that's going to be whatever's on the top of our queue. And then we say, okay. And then from here, what we want to do is say, okay, well, what we want to do is we're trying to keep track of the number of like the max color path. We need to maintain that as we propagate through here. So to do that, we're going to define a dictionary, and it's also going to be a collection here where we're going to have a particular node pointing to its colors. And so I think the best way to do this is this way. So so for every particular node, we're going to have a corresponding dictionary, and it's going to have a particular integer, and this is going to map to, okay, for every node, we're going to have a dictionary at that node, and it will say, okay, there is, at this point in our graph, color 1 will have like a particular count. So say if at this point in our graph we already saw like 3 different colors of red, we want to put 3 here. And then color 2 is going to have like 5 different colors. And say color like 3 has like 6 different instances. Oh, I can't spell. Okay, and so we're just going to keep propagating that color as we're iterating through this graph in this dictionary. So say at this particular node, we're going to have a corresponding dictionary with a particular value. So for I in this particular range of n. Great, and so that's our dictionary, so we can maintain the longest color path that we're trying to establish here, the largest color value. And so let's go ahead and do that. Oh, there, my music's too loud. And so what we'll do is we want to say, okay, let's update that value for this particular node because it has an associated color with it. And so in our dictionary, at this particular node, we're going to want to increment the value for this dictionary. And so we want to get inside here. At this node, we're going to get the color that corresponds to this node by looking up our colors array here. So this gives us the color of this current node. And we want to add 1 to here. Right, this colors. Awesome. I can just do pop there. Great. And so from here, we're going to want to add to our count because we just visited this node. And so we want to include this. And this is what, once again, is used to detect our cycles using Collins' algorithm. And from here, we're just going to want to iterate through all of our neighbors. So for every neighbor in our graph, we do that by looking at our adjacency list for this particular node. Okay, and so from here, as we're iterating through our neighbors, we can see, okay, where can we go from here? We're going to want to add that corresponding neighbor to our queue. So let's do queue.append. And we're going to want to put that neighbor in our queue. And so we can pop it off in the next iteration. But we're only going to want to add them to that queue if they satisfy the property of, okay, they don't have any more dependencies that we haven't already resolved. And so because every single time you visit and you kind of update a particular node, that counts as resolving that dependency for a particular node. So you can say, okay, well, in this case, since we just visited this node, which this neighbor is dependent on, because this current node is a prerequisite for this neighbor, then we can decrement this neighbor's in degree. And so we can do minus equals 1. So after we decrement it, if it hit 0 here, then we can add it and visit that graph. Okay, and so from here, what we're going to do is we want to also be able to address the color, so the largest color path here that we've been maintaining through this kind of depth first search or through while we're iterating through this graph. And so to do that, we're going to want to look at our dictionary and say, okay, we want to say we're at this particular node and it had 2 different parents here. And so say that this node 1 had the dictionary of, okay, like it had at this point, color A appeared like 5 times and color B appeared like 7 times. But then at this particular node, we had color, oh, that's not a good color. This is brighter, so you can see it better. So, and then we had color A appear 20 times, and that's it. Well, then at this particular node here, say that we're currently on this graph and we're looking through its neighbors. So this might have already been updated so that this node, it already has a color A of 20. So then as we just resolved this dependency for this particular node, and now that this, since it has an in degree of just 1 right now, since this dependency has already been resolved and we had decremented it, now that we just resolved this dependency, we'll decrement this down to 0. And so we'll be able to add it to our queue and now process this node. But first, we're going to want to update its dictionary values here for kind of the current largest color value path that we've been propagating through this graph. And so we'll want to update it with, okay, we want to take the maximum of color A. So the max paths for the color A would be down this route by going through here. So we want to keep that and not use this. but we'll want to update it so that it also has color B of 7 at this value. And that's the max largest color value for the color B at this particular node. Okay, so it might take a bit of drawing to figure that out, but this is how it made sense to me. And so through here, what we're going to do is we're going to want to update that. So let's say, okay, at this node, we're going to want to, let's see here, iterate through all the different colors. So for every color in our parents' colors, so we can do that by saying, okay, at this dictionary for this particular node, we're going to want to iterate through all of its colors. So I think this works. And so this will give us all the colors for our parent. So when our parent had a color A and color B, we're going to iterate through color A and color B. And so for this neighbor, so for at the dictionary for our neighbor, we're going to want to update the colors to the maximum of either whatever has currently been updated. So in our previous example, we showed that, okay, we might have processed a parent node first and updated our neighbor here. So we had taken all the maximums and added like that color A equals 20. And so we want to compare color A equals 20 with our other example, which was color A equals 7. And so we do that by saying, okay, the dictionary for our current node at this particular color. Great, and so that's how we maintain that color path, and we can keep saying, okay, this is the largest color value at this particular node. And so I believe the last thing that we're going to want to do is we need to also be updating our response here, because we haven't even used this yet. We've been maintaining this large color value, but we haven't been updating our response. And so through here, what we're going to do is we're going to want to set our response to, I'm just trying to think, the values. So because every node here can have like 4 different colors that is associated with it. Like in this chain here, there's just 2 different colors. So at this particular node, it would have like a count of 2 for red, and at its dictionary there's a blue. So its dictionary for here would be like, okay, blue is 1, and then red is 2. Right? And then it would get updated here so that red becomes 3. But we're going to want to maintain, okay, what is the largest one? So we'll want to set the response equal to 3 here, because you just want to iterate through these values. Okay, and so our response will be equal to the maximum value for all of the colors. So that would be the maximum of, at this dictionary for this particular node, all of its values. There. So I think all this, oh, something's wrong here. We returned 1, but we selected 3, so something might not be getting updated. So we might want to be comparing our current response to that. Oh, yes, so we want the maximum of our what we currently have and compare the maximum of that. There, let's try running this. Great, I can't believe I got that right. I had just solved it like an hour ago, but I didn't think I could explain it in one take. So yeah, so basically, just to reiterate all this, we first want to just get the number of nodes that we're dealing with in our particular graph. We want to represent our graph with an adjacency list, and at every single particular node, we will want to have a corresponding integer that represents the number of incoming edges or the number of prerequisites in order for us to evaluate that node. And so from there, after we've built out our graph and we know the number of incoming edges, we're only going to want to add to our queue and process the nodes that have 0 incoming edges, because that, if you think of a tree, like the root would have no incoming edges. And so therefore you can process that node in a DAG-like manner where you're kind of starting with the nodes that have no prerequisites, take class A because it has no prerequisites, and then take the classes that were dependent on that first class. And so let's continue iterating. We want to maintain a count that represents the number of nodes that we visited, because if we have not visited, like say there's 5 nodes in our graph, we need to visit all 5 nodes. And if we didn't visit all 5 nodes, that means that there's a cyclic dependency because it was never able to have 0 incoming edges or 0 prerequisites. So we just know that, okay, there was a cycle in this graph. But we also want to maintain a dictionary, which just means, okay, at every single node, we're going to have a corresponding dictionary that has a particular color and its associated count of how many, at this particular point in our graph, how many colors have we, or how many instances of a particular color have we ran into. And so then we just want to maintain, okay, this is our response is just whatever color appeared the most often at this point in our graph. And then we just want to, and this is kind of typical depth first search code where we just iterate through every neighbor or every single node that we can go to next in our graph. And we'll want to update and just maintain the maximum like color value for every single color and the number of occurrences that we've seen for that node. So that say if this child node has 2 parents, we just want to take, okay, if color A appeared 5 times for parent A and color A appeared 20 times in color B, let's take the 20 rather than the smaller value. And so then we want to decrement for that neighbor the incoming edge, which was his parent, because we just processed that parent. So this child node no longer has that prerequisite for its parent. And so then if the child no longer has any more prerequisites that haven't been completed or resolved yet, then we know that we can process it. Okay, and so that's a hard LeetCode problem using Kahn's algorithm. It's a very famous algorithm. I remember learning about it, I think, in my networking class, and then also my like second or like harder algorithms class that I took. So it's very kind of famous computer science problem. So it's great being able to apply it to this. So yeah, I hope that helped, and I hope you enjoyed my explanation. So yeah, good luck with the rest of your algorithms. Thanks for watching.